Now that we have the fundamentals of vectors behind us, we're going to take a look at vector-valued functions. We can describe curves in three-dimensional space using vector-valued functions. We're going to use a parameter like t, typically represents time, as our inputs for these functions. The outputs are going to be vectors. When we consider these vector outputs, we're able to examine things like the motion along a path in three-dimensional space. We'll use two different ways of noting a vector-valued function. We can write r of t equals the vector x of t, y of t, z of t, or we can write it in terms of the unit vectors I, j, and k, where each coefficient is one component of the vector-valued function. Notice that we use a single independent variable, the parameter t, as our input. So vector-valued functions look a lot like parametric functions. However, in a vector-valued function, the output is a vector, which means that as t changes, those vectors are modeling how a point moves along a curve. Each point on the curve serves as the head of a position vector, and the orientation and direction of those vectors is important. When considering a vector-valued function, we have to consider which values of our input parameter t will produce a vector as an output. In other words, we need to think about the domain of a vector-valued function. So if r of t is equal to the vector-valued function x of t, y of t, z of t, then the domain of r of t is actually going to be the intersection of the domains of all of its component functions. Let's take a look at the vector-valued function r of t equals cosine t, sine t, t. If we think about what this might look like, if we just consider its x and y components, we know that cosine t, sine t is a circle. However, the z component is changing over time as well. This means that this curve looks like a spiral, and we can see in the animation that as t increases, we move up the spiral. The green arrow in the animation represents the vector output of the function, and the red dot represents the head of that vector. Let's see if we can find a vector-valued linear function that describes the intersection of the two planes we see here, x plus 2y plus z equals 4, and x plus 2y plus 3z equals 6. So in order to do this, we know for a line, we need a point on that line, or the head of a vector. So we need some vector that indicates a point on our line. And then we also need a direction vector. So let's go ahead and see if we can find a point on our line. We're going to do that by let's let y be 0. If we have y equals 0, then we get that x plus z is equal to 4, and x plus 3z is equal to 6. When we subtract those two things, we're going to get that negative 2z is negative 2, so z is equal to 1. So now we have that y is 0 and z is 1, and if we plug that in, we get that x plus 1 is equal to 4, and so that tells us that x is equal to 3, and if we use the other equation, we also get that x plus 3 is equal to 6. So either way, we see that x is 3, which gives us that the point on our line, or our starting vector, is going to be the vector 3, 0, 1. Now we need a direction vector. Well, we know that the vector n1, which is 1, 2, 1, that is parallel to, or perpendicular rather, to this first plane because it is the normal vector for that plane. Similarly, the vector n2, using the coefficients from the second equation, 1, 2, 3, that is going to be perpendicular to the second plane. Our direction vector then is going to be perpendicular to both of these. In other words, we can use the direction vector as the cross product of those two, since each of those is perpendicular to a plane by definition. We know that it must be perpendicular to our direction vector, which lies in those planes, and therefore we can use the cross product to find that vector. So we're going to do 1, 2, 1. 1, 2, 3. And when we do that, we get, let's see, that's 6 minus 2i minus, and we get 3 minus 1j plus 2 minus 2k. So we get the vector 4, negative 2, 0 as our direction vector. So now we have a line and a direction vector, or we have a point. So our line is going to be, we start off with our point, 3, 0, 1, and we add to that our parameter t times our direction vector. And we get that this is 3 plus 4t minus 2t and 1 as our line. So we can see on this line that the z-coordinates are always 1 and the x and y coordinates are varying with respect to t. Note that if we'd started with a different point, or if we had chosen our direction vector by reversing n2 and n1, we would get a different parameterization. So this answer is not unique, but it is still correct. All right, so let's see if now we can find a linear vector valued function that describes a line segment. So we know for any line, we need a vector to start it off with and a direction vector. So our initial vector here is going to be the same as our initial point, p. So it's going to be the vector 2, negative 1, 0. Our direction vector for our line is going to be the same as the vector pq, which we can get by subtracting, we can do q minus p component-wise. So we get negative 1 minus 2 is negative 3. 3 minus negative 1 is 4, and 2 minus 0 is 2. So now we have the components that we need. So we can start off with our function r of t. It's going to be our initial point, p, plus our parameter t times our direction vector. And combining that, we get 2 minus 3t, negative 1 plus 4t, and 2t. However, that describes a line. Here, t can be any value, and we're going to end up with much more than our segment, our desired segment pq. So we need to restrict the domain of this. So we know that when t is 0, if we look at r of 0, we're just going to get to negative 1, 0, which is p. We want to find out for what value of t do we land at q. So if we look at, we're looking to figure out, not negative 3, negative 1, 3, 2, when does that equal our function? And we can just look at that from a component perspective. If you look at the z component, 2 equals 2t, we get that t is equal to 1. And we can check that with the other ones. Let's look at negative 1 equals 2 minus 3t. That if we subtract, we get negative 3 equals negative 3t, and we confirm that t equals 1 works for the x value. And then if we do the y value, 3 equals negative 1 plus 4t, and we get that 4 is equal to 4t. So what does that tell us? Well, that tells us that our function is this function right here, but we have to restrict the domain. T has to be only values between 0 and 1. At time 0, we're at p. At time 1, we're at q. That's the only segment that we want to carve out. And so restricting the domain gives us the segment that we want. So this time we're looking for the domain of a vector valued function. And we know that the domain of a vector valued function is the intersection of the domains of each of its component functions. So if we look at the domain of the function x of t equals 4 over t minus 3, we see that t can't be equal to 3. T is not equal to 3. So in other words, the domain of this is everything except 3, which we write as negative infinity up to 3, and then 3 to infinity. the domain of y of t is 1 over t plus 1. Here we see that t cannot be negative 1, so we write that as negative infinity to negative 1, union negative 1 to infinity. So now we're looking for the intersection of those two, where they overlap. So we can, if we draw a number line here, and I'm going to mark this domain in pink. So the domain of x of t is everything except 3. The domain of y of t is everything except negative 1. So in other words, we're looking for where these two overlap. Well, they don't overlap at negative 1 and 3. And so our domain for r of t is going to be negative infinity to negative 1. This stuff over here where they overlap, and then from negative 1 to 3 where they overlap, and then our last section where they overlap from 3 to infinity. We're excluding negative 1 and 3 in the domain. Okay, here we have a vector valued function, r of t equals 3 cosine t, 4 sine t, 0, and we want to show that it actually lies on the surface x squared over 9 plus y squared over 16 equals 1. So let's think about what we know about each of these things. First of all, r of t equals 3 cosine t, 4 sine t. If you were to graph a few points of that, you could see pretty quickly that that is just going to be an ellipse. The z coordinate of 0 tells us that it is lying in the xy plane. We also know from what we know about quadric surfaces that because z is missing from this equation, this is a cylinder. And given its equation, this is actually an elliptic cylinder. In other words, the traces of this are ellipses. So we're trying to see if the particular ellipse that we have lies on the elliptic cylinder. So let's see how we might go about doing that. Well, let's think about this as x, and let me use a different color here. We're going to think about this as x, and this is y. So if we plug those into our equation, we get 3 cosine of t squared over 9 plus 4 sine of t squared over 16, which is, of course, 9 cosine squared t over 9 plus 16 sine squared of t over 16, which is cosine squared of t plus sine squared of t when we cancel the 9 and the 16. And so we get 1, which is correct. Cosine squared plus sine squared is 1, which is what we wanted up here. So we see our curve given by our vector valued function is on the surface that we have, our elliptic cylinder. All right, in our final example, we are going to be minimizing the distance from a given vector valued function, r of t equals t squared, comma, 2t. That comma's in a really weird place, but we'll ignore that right here. T to the point p0 equals 0, 1, 3. All right, so what we're going to do, our goal here is to minimize the distance, which hopefully you recognize as a calculus problem, an optimization problem. But we're going to make our lives a little bit easier by recognizing that minimizing the distance is exactly the same as minimizing the distance squared. So if we write the distance squared from p naught to the curve for any value of t, that is going to be given by t squared minus 0 squared plus 2t minus 1 squared plus t minus 3 squared. Right? If we put a square root around all of that, we would have the distance formula, but since we're squaring it, we don't need the square root. And so if we expand this out, we get t to the 4th plus, and then we get 4t squared minus 4t plus 1 plus t squared minus 6t plus 9, using FOIL on the second two terms as appropriate. And we can tidy this up a little bit. We have t to the 4th, and then we have 5t squared. minus 10t plus 10. And now we think back to calculus and we take a derivative of this. So this is d of t, so d prime of t is going to be 4t cubed plus 10t minus 10. And we set that equal to 0, and we can simplify that to be 2t cubed plus 5t minus 5 is equal to 0. This is a cubic equation. It has only one real solution. We can use some technology here. So graph this in Desmos or on your graphing calculator. We see that t is approximately 0.797. And so now if we want to find the point on the curve, our curve point, r of 0.797, is going to be 0.797 squared, 2 times 0.797, and then 0.797. And if we actually figure out the minimum distance, our minimum distance, plugging back into this equation for d of t and taking the square root, that distance, again, I'm using a calculator to do this. These numbers are not nice round numbers, but we get that our distance is approximately 2.368 units. We don't know what those units are, but it's about 2.368. So we now have a new kind of function, the vector valued function, available to us to explore what's happening in three-dimensional space. And we know that these behave a lot like familiar parametrized curves that we've seen in two-dimensional spaces, where each coordinate of those functions behaves as a function of the parameter. And we're going to see over the next few videos that we can do calculus on these vector valued functions, and we can use them to explore notions of position, velocity, and acceleration.